So hi, my name is Chongur, and I'm here with Toby. We're just starting our third year in the Imperial College London undergraduate scheme, and we'd like to talk a little bit about the project that we've been working on for the past few months. So what is VoxelCAD? It is a collaborative voxel-based CAD tool, which in our context, it means that we are building 3D models out of cubes in the browser with a programmable functional domain-specific language, which we found to be very useful for describing three-dimensional constructions. Another link to functional programming is that it's in fact written in Elm and Haskell, and a little bit of TypeScript for performance reasons, not much. It's actually work in progress, so it's a little bit rough around the edges somewhere, but we've got some things to show. So before jumping to the actual technical details and the presentation, let me talk a little bit about the context of the project, so why we even bothered building something like this. So a lot of people use Minecraft as an artistic canvas. They build the very big artistic creations in Minecraft, and these tend to get very very big very quickly. Some people actually make a living out of this. So this was built in Minecraft, and as you can see, it's very involved. It's quite big, and there's a lot of geometric structures in there, which we identified and thought that we could build tools that make building things like this easier. So actually, at the moment, there exist tools for doing that sort of stuff, but most of them are within Minecraft, and therefore they're fairly limited in their usage because they're limited by the Minecraft rendering engine, and Minecraft doesn't really have an API, so it's all a bit hackish. It's slow, clunky, and you don't really get immediate feedback. So we thought that an interesting approach to building 3D environments would be by implementing a functional domain-specific language. It is pure, there's no global state, so if you have a script, you run it twice, you get the same answer. Fairly straightforward. It composes very nicely, so you have two scripts, you just put them together, and you have now one script, which does the same thing. It's easy to understand, even without programming knowledge to begin with. And it's a Lisp because we will write the parser later. So let me show you a quick demonstration at first, and then we'll talk a bit about the technical details and then a more involved demonstration later. Just a really quick idea of what it looks like. So yeah, at this resolution, the sidebar is actually quite big. So we have an editor window here, and the output of our scripts. So the idea is that we get immediate feedback. So I can say, I want to scale evenly a cuboid, actually a cube. Let me move around a little bit. So I just created a cube. This is made out of smaller cubes, as if it would be built in Minecraft. That's a bigger cube. Let's rotate this by, that around the origin. So I can rotate the cube. This is something that you can't really do in Minecraft. Rotate it on another axis, all three axes. Might want to put it in the middle. I can scale it up a bit. Works just fine. So this is the first approximation, first idea of what the tool is capable of doing. I can put a cylinder in there. Move it up a bit. So we have these two constructions here. Yeah, so that's the first idea. Let us talk a little bit about some technical details, how the underlying things work, and then later on continue with the more involved demo. So.
All right. So obviously this is a 3D-based world, so we've got these quite complex 3D geometries. So obviously the number one question that comes to your mind is, how do we represent these geometries in a nice programmable way, and not only that, in a way that will be easy to implement in a purely functional language? So one of the things about Minecraft is that it's solid. Every single block is completely solid, so we decided to find a representation scheme that mimics that. So we found constructive solid geometry is a very, it's a neat means of representing shapes in the 3D world. So first off, we start off with these primitives. So a cylinder, a sphere, cuboid, cone. We can just represent this as a simple algebraic data type, like that. This gets a bit more interesting when we combine these with Boolean operations. So this here is a subtract operation. On the left we have a cylinder, on the right we have a cube. And you notice that when they combine, you get a more interesting shape. And this, in fact, scales quite well to when you have, you can create a sort of tree-like structure. Wait, I was going to say that there are three operations you can do in this scheme, which is union, intersection, subtract, as you might expect. But this can scale up to a tree structure. So at the leaves, you'll have these primitives. And then, but you can also define a combination by an operation on two subtrees. And of course, you have to add some transformation to each node to make it usable in an editor. But yeah, that's pretty much how every single shape in our universe is described with this very simple data structure. Another technical challenge is you might have seen that we have these abstract descriptions of shapes, but in the editor, you were seeing cubes. So it's not a simple problem. There's obviously a naive method of going from a mathematical description of a shape to a voxelized form, which is simply iterate over the bounding box and check whether it's contained within the abstract description. But that's incredibly slow. And since we're in a browser, we can't do that. We have to come up with a much faster method. So our approach was hardware-accelerated voxelization. So the way we do this is by utilizing a property of convex solids, or all of our primitives are convex. So that means that they can be uniquely determined by two depth maps from opposing directions. So what we do is we use the WebGL API to, we use the WebGL API to take orthographic depth projections, returning low resolution depth maps from two directions. And it might be a bit difficult to determine from this diagram, but if you imagine the numbers on the sides represent the depth, then, and the red line is the mathematical description of the shape, then you can sort of see how the ranges can define the resulting voxelization. And this system ends up being surprisingly robust, and it can scale up to very, very large and detailed structures. So I guess we're going to give a longer demo now to showcase what you can really create in this DSL. Chongo is going to be actually doing the coding. But so I think the first thing we should show off is how the CSG sort of is done in this universe. So quite simply, you just use an intersect operator, and you're going to intersect the two solids that were there before. Oops. What did you do? Oh.
Maybe the size of, try union first.
Oh yeah, okay, union. Okay.
Okay, so cone is down there.
Oh, the cone's at the bottom. So you might want to move it up a bit. But that's quite simple to do. We've provided a lot of functions such as like move up and scale even, and that makes defining these things a lot faster. You might want to get rid of the old regions. I don't know, but yeah. So that's the intersect. We also have the subtract and the union. But that's not very interesting. These are just like small shapes, and they're just a single operation, which is union or intersect or subtract. But what we really want to do is create something that is more programmable. Oh my God, what the hell is that?
Well, I mean, that's fine.
I think that's actually
correct.
That's actually correct.
Yes.
Yeah.
Okay.
just looks a bit strange because the regions are so closely close to each other. You might want to like, oh whatever, you might want to scale the cylinder down a bit. But yeah, the task we're going to do today is to make a very simple castle. So I mean, we're talking about Minecraft here. If you've ever played Minecraft, one of the things you do is make a castle. It's pretty obvious. But as with all programming, we want to break that down into smaller tasks. So first off, let's make a tower. Why not? So a very simple tower primitive could be composed of a cylinder and a cone, with the cone on top of the cylinder. And that can be described very, very simply, just like, yeah, so we'll obviously have to move the cone up a bit to sit on top of the cylinder. And we probably want it to extrude a little bit above the cylinder to make it look like a tower shape. Otherwise they would just align perfectly. But we'll see feedback of this once the code is in a state where it can compile. Which shouldn't be, okay.
I want to scale that up.
Yeah, you might want to scale, make it really big. Okay, so there we go. And that's a very simple tower primitive.
Why not move the left a bit as well when
Oh yeah.
Good point.
Sure, why not? Well, the first thing we're going to do is place these towers at the points at which we might define towers on our castle. Should we define a list of points defining the towers of our castle?
Sure.
So that's very simple. The DSL we've defined is has very few operators, and as such, it's a little bit clunky to write right now. But you can express a lot of things with just very simple components. So we'll have maybe 3 is enough points, and then we'll paste a tower along each point. So this is it's just very simply mapping over the list of points. It's a very common functional, it's a functional function really, but yeah. So we can quickly define a function to takes a position and then it pastes the tower at the point.
So yeah, might wanna.
Oh, is that working or?
So I'm going to map tower at over the points and want to union them.
Oh yeah. So once we've mapped the tower at function over the points, what will result is a list of regions. But that's not very good. We sort of want one region, so we can just union these together. So that should be done in a short while. Wait, are they there? Or?
That's too far apart.
Yeah, maybe they're too far apart.
Oh yeah, make put it like 50 or something. Okay, there we go. So it's quite simply now we have the towers which our castle will require, but that's not enough really. We need walls between these things. So let's first define a function which makes a wall between 2 points. That makes sense. So define a function walls, which takes 2 points and then draws a wall between them. So we can use the road tool. It would normally draw a road, but you can sort of think of a wall as a very tall and very narrow road. Yeah, it'll make sense when you see it up here, you know. Yeah, and so another problem we've got to think about is we sort of want the whole castle to be connected all around, but what we've got is a linear list of points. So we want to connect the head of the list with the tail of the list, which, I mean, we could just append the head and duplicate at the tail, but I think a much nicer way of doing that is to rotate the list and then zip with a road operator, or the road function. So first we should define a function to rotate a list. So take the head of the list, put it at the back. And that's super simple. We've got functions to do this. Okay, and that's it. So now we probably want to...
These brackets keep accumulating.
Yeah, the brackets at the bottom are not good. And one of the things that we obviously want to add to this is a more sophisticated editor to, syntax highlighting and et cetera, et cetera. Oh, do you have a question?
Yeah. Why do you need still going to still wall going to straight?
Yes.
Why don't you use
Special case.
It's okay. So it's a special a straight line is a special case of a Bezier spline. We should really have is a linear spline, but we haven't added. It's just like it's a specialization. We can implement it simply with more abstract methods. But yeah, another question.
So Bezier curve is not convex.
So a Bezier curve, our Bezier function takes a list of points and then smoothly interpolates along the curve. We can show that off maybe a little bit later. We might have to cut this demo a little bit. I guess you could just sort of do a bit of power typing and try and get to the end. We could maybe even come. Actually, no, that's not going to work. But yeah, so the Bezier function returns a smooth interpolated spline. Yeah. Does that answer your question? I'm not sure what you're talking about. Convex.
Your optimization for doing voxelization depends on shape being convex.
Oh yes. So that's a good point. So if we were to naively create a set of polygons along a non-convex spline, then we would end up with a concave spline. Then we would end up with a concave region or a concave shape. So the way we get around this is by sampling the spline at a certain number of points and then making convex primitives along it. So you can represent a concave shape out of convex solids, and that's basically the sort of philosophy of this. You might want to add more points.
Yeah. All right.
Just so we can see the walls in. Okay, there we go. So the walls aren't.
Walls off the ground.
They are off the ground right now. We might want to move the towers up a bit. In fact, I think they're actually the walls are on the ground and then the towers are underground because there is no ground. So have you done it?
Let's do it.
Okay, let's do it. And we'll probably have to. Well, once we've done that, then we'll cut the demo short and we'll move on to the rest of the presentation. Because you've seen pretty much all the features of our thing, apart from the whole Bezier spline interpolation, which is quite cool, but we don't have time to show it off right now. All right, cool. There we go. That is a simple castle. The cool thing about this is that it's very programmable, so all of the parameters are modifiable. You can move the pointer up and off the ground, etc. So if you put one of them at give one of them a height of 10 or something like that. Okay, so now we move it up, and it doesn't matter. We can program any parameter of this castle and add more points, etc. etc. But I think we should cut this short because we don't have much time left. So let's move on to the rest of the talk.
Yeah. So as we said, we implemented this in Elm and Haskell. So the way we did that was the front end of the web interfaces is all Elm and TypeScript, and the back end is written in Haskell. So we just like to give our impressions on Elm, just to. So Elm is a new programming language for web applications, which means that the language has a very good notion of a very good understanding of what a web application looks like. Which means that you have good support for single-page interactive HTML applications. Unfortunately, our tool is fairly static, and most of the interaction is going on at a lower level, so we couldn't really benefit from that. The language is similar to Haskell, but there are some inconvenient differences, which are mostly just a lack of higher-order abstractions and you don't have type classes. You can't do generic programming, which is something that we really missed because, one extra point is that, as a good point, the language is a really predictable runtime system. So if you want to do some low-level optimizations, you can exploit the fact that you know how the data is going to be represented. Just a really quick point on generics, which is something that we really like in Haskell. You're able to define your data structure and then derive the generic, and using a library such as ASON, you can derive the serializer and deserializer code. This is something that Elm doesn't have, unfortunately. We really missed this. The way we tackled this problem was by writing a generic library for Haskell and derive the Elm data structures, and the Elm serializer is just generated by the Haskell code. So that's sort of a workaround. It works quite well. We wish Elm also had generics. A few things on the future work of this. We would really like to have a more usable editor, or a usable editor, really. So auto-completion, syntax highlighting, those would all be nice. We were also thinking about some more interesting type system for the scripting language. At the moment, it's just untyped, and it just blows up if you do something bad. We want more mouse support. That would be useful for general-purpose CAD editing, and we think that it could be used for teaching programming to little children who are very interested in Minecraft already. It's very popular, and so we were thinking about how that could happen. And I think that's what we wanted to talk. Thank you. Are there any questions?
I had a question. Maybe your type DSL point is an enter and enter. Why are you defining your own programming language?
You mean why a DSL as opposed to an EDSL, or so?
I would say library, but me.
Okay. So one of the main reasons we went with this language on its own concept was that the embedded approaches are all you have to go through this compiling step, and you have to write the host language, which might provide its own abstractions, which can be nice but can be a bit distracting as well for people who really just want to focus on. That's what I think. Yeah. All right.
You need to find something more convincing.
We enjoy writing programming languages. I guess that's another.
Don't you convince you, then you convince themselves, right?
Yeah.
So one thing that would be good if you could detect collisions between your shapes. So for example, you can say, I want to be warned if some shapes are colliding. I mean, it should probably be easy with all the underlying stuff you've already done. Or that you can also do stuff that is maybe where you can say, if you want to build a tower, I want to put the cone directly on top of the cylinder with no gap. There's nothing in between, so stuff like that.
Yeah, that's a good point. I think the second point, it's a bit hard to represent the notion of on top of another thing, because you can have carved out structures. It could be like a really arbitrary shape. We sort of went with this simple tower thing because that's quick to code up, but you can really get. You can represent Bezier curves and all sorts of.
You could define all your structure with two attachment points, one before, one after. And the top would be after, then could be just.
Yeah,
we sort of the sequential composition of the tower and the top.
Yeah, that's good. We actually already have, as an optimization, we use an axis-aligned bounding boxes, which I guess could be used to stack these things on top of each other, if that's what you're suggesting.
Maybe I missed from the point, but why do you voxelize the result of the CSG? The other methods like this, is it because of speed?
So yes, I think our original motivation was for interaction with Minecraft. So actually, there are a few features that we didn't show off. So you can import from Minecraft, and you can also export back to Minecraft, which really lends itself to this cube-based voxelized rendering concept that we have here. Yeah. I think that's
speed.
And yeah, speed.
Right. Let's thank our speaker.